This video is about directional derivatives. And directional derivatives are a generalization of the concept of a derivative of a single variable function. So let's just jump straight to the definition. So let's say that A is some open subset. Actually, it doesn't. Let's just say that A is some open subset of Rn. Let's use Rn. Okay, and let's say that f is a function from A into Rm. A is an open set in Rn. Okay, suppose that A is in A, then given U in Rm, with U not equal to the 0 vector, define this symbol f prime of A semicolon U to be, so this is a definition, the limit as t goes to 0 of f of A plus tu minus f of A all over t, provided that the limit exists. Okay, let's take a look at this expression. So f is a function from from an open subset of Rn to Rm, and A plus tu, right? A is in Rn, U is in Rn, A plus tu is in Rn. F of that is a vector in Rm. F of A is a vector in Rm, so the difference, this numerator, is in Rm. And this is just 1 over t times that vector, right? T is a scalar. So this is, so each of these things that you're taking the limit of is in Rm, and then you're taking the limit of those vectors as t goes to 0. So the result is a vector in Rm. Okay. Oh, sorry, this should say Rn. Okay. Okay. So this is called the directional derivative. This is called the directional derivative of f at A with respect to U. Okay, let's just do some examples. And this is a very general definition, but let's look at the case where n is 2 and m is 1. So in this case, we have a function from R2, or a subset of R2 to R. So let's say that you have a function from R2 to R, which is given by f of x comma y equals x times y. Okay. So let's say that A is some vector in R2, A1, A2. And let's say that I take the unit vector u equals 1, 0. Okay, what's the directional derivative one second. about that. So the directional derivative of f at a with respect to u is, well, according to the definition, we need the limit as t goes to 0 of f of a plus tu. Okay, so a plus tu is a1, a2 plus t times 1, 0, and that's a1 plus t, a2, right? So it's the limit of f of a1 plus t, comma, a2, minus f of the vector a, so f of a1, a2, all over t. And this is, okay, f of xy is x times y, so this is the limit as t goes to 0 of a1 plus t times a2 minus a1 times a2 all over t. And this is equal to the limit as t goes to 0, so you distribute the a2, and then you cancel and you get t a2 over t, the t's cancel, and you evaluate the limit to be a2. Okay? And let's just do another example with the same function, but with a different vector. With respect to the vector v equals 1, 2, okay, well, so we just use the same definition. A plus tv is a1, a2 plus t times 1, 2, and that's equal to a1 plus t, comma, a2 plus 2t. And so therefore, the directional derivative f prime of a with respect to v is the limit as t goes to 0 of f of a1 plus t, comma, a2 plus 2t minus f of a1, comma, a2 all over t. And this is equal to the limit as t goes to 0 of a1 plus t times a2 plus 2t minus a1, a2 all over t. And I'll let you just evaluate this. This is equal to a2 plus 2a1. Okay? So those are some examples of directional derivatives. And it's, in general, I don't think the general definition of directional derivatives is that illuminating. However, in the case where m is 1 and the vector u is a unit vector, there is an interpretation. So in the case, kind of geometric interpretation. So in the case where m is 1 and u is a unit vector, there is a geometric interpretation which is, okay, let's just do an example. So let's say that f is a function from R2 to R. Okay, then you can graph, if you imagine R2 like this, and then here are the axes, and then you have the z-axis like this, and you imagine graphing the function. So let's say that's the graph of f, right? And let's say that you're at this point. Well, can I zoom in? Okay, let's say that you're at this point a1 comma a2. Well, above that, you have the point on the graph of the function. That's the point a1 comma a2 comma f of a1 a2. Right, that's a point in R3, and here I'm identifying R2 with the xy plane in R3, which I technically shouldn't do, right? This point is technically a1 comma a2 comma 0. But nevertheless, okay, so, but when we're thinking about functions from R2 to R, I mean, typically you want to think of the, right, we're thinking of the xy plane as just the R2, and then the output axis is R instead of, R3. Okay. So, anyway, you have a unit vector, let's say u, let's say this is our unit vector u, okay, then the idea is you can take the plane that is parallel to u and intersect it with this point a1 comma a2 comma f of a1 a2. So you take this plane that's parallel to u, and what you get when you intersect that plane with this surface is you're going to get this curve. So this curve is the intersection of the surface, let's call this surface S. The intersection of S with this plane is this curve. And what's going on is, so you have this vector v, which we can think of as starting from this red point, and you're looking at how fast this function, so now you have like a function of one variable t, and you're taking u to be a unit vector. So if you imagine this, drawing it like flat, you have this point a1 a2, and then this unit vector u, and then you have this curve lying above it. Well, this is okay, I guess I should have made it more like this to make it match. And now this is like an ordinary derivative. Right? This is like the derivative of this function. Because if you take f of a1, a2, you're at this value, and z, and if you take, right, so this is f of a1, a2, and then if you take tu, you're here, and then if you plug it in, you get this point here. So this would be like f of a1, a2 plus tu, right? And then when you take the difference, you're just taking the difference in the z values, and then you're dividing by t, which is the horizontal distance along this cross section. And so the limit as t goes to 0 is the rate of change of this function. Or you can think of it as the slope of this line, this tangent line, through this point. Well, in this case, it will be 0. So in the case where in the case where, so this is analogous to just ordinary derivatives, right? It's the slope of the tangent line to the graph, which is the cross section. This cross section at the point A1, A2. And in the case when n is 1 and m is 1, and well, in this case, your vectors in Rn are just going to be real numbers. If you take the vector u to be 1, then you just get the limit as t goes to 0 of f of, okay, a, right, plus t times 1 minus f of a all over t. Well, this is just the ordinary derivative, f prime of a. Okay, so this is a generalization of derivatives from single variable calculus. Okay, so that's it for this video. This is an introduction to directional derivatives, and then in the next video we'll talk about how you can relate directional derivatives to the derivative of a function of several variables. So before we talked about how if you have a function from Rn to Rm, if it's differentiable, then there's this matrix df of a, and this is a m by n matrix. And in the next video, we'll relate this to the directional derivatives that we learned about in this video. Okay, thanks.